Good morning, everyone. Today I'm going to talk about temperature control inside an enclosure. So, when we have a valuable artifact to protect, we keep it inside a storage box or a display case, and we hope that this enclosure will keep the temperature and humidity inside in a more or less constant manner. The outside temperature and humidity change, it goes up and down, and we hope that this box or the display case will buffer the fluctuations that occur externally. Now the question is uh, how to understand this buffering capacity of an enclosure. A usual experiment that we do to uh, to investigate an enclosure is to just take two data loggers and place one outside and the other one inside. So these are the results of those experiments. In these figures, the horizontal axis are the time in hours and the vertical axis are the temperatures. These are for three different boxes. The orange curves, the orange dots are the external temperature and the purple dots are the internal temperature. So we can see the external and internal are different, probably because the box produces some buffering. But looking at this data, it is very difficult to say which of these three boxes has the largest buffering capacity. It is because these are not subjected to the same external fluctuations. If we want to do that, we have to use a lot of data loggers. But usually what we do is we just use two data loggers and measure the internal temperature that occurs as a response to different external temperatures. So it is very difficult to compare them, but from these data sets, we can calculate something else. From all this, we can calculate this. So here, again, we have the internal and external temperature as functions of time, but the red is a hypothetical external temperature and it goes around zero, that is it's the temperature deviation from the mean value. The black dashed curves are the internal temperatures that is predicted based on these results. So when we have these three figures, it is very easy to compare because the red curves are the same, and just by looking at this we can say that this box has the highest buffering capacity, this one has the lowest buffering capacity, and this one has a moderate buffering capacity. So the question is, how do we go from here to here? To do that, we need to understand how heat transport occurs into an enclosure and how that results in temperature changes. So this is an schematic diagram of a box. Te is the external temperature, Ti is the internal temperature. So here uh, blue is external, red is internal, and then the wall of the enclosure is also has a temperature. It is called we call it Tw. Now for simplicity we can assume that internal temperature is constant throughout this region, wall temperature is constant throughout the wall, and as a result of these temperature differences from external to the wall to the internal, heat transport occurs. There are different heat transports. This is heat transport from the external environment to the internal environment, heat transport from internal environment to the wall, heat transport from external environment to the wall. Now, The heat flow rate is proportional to the temperature difference and proportional to the surface area and also proportional to the heat transport coefficient. When we have a heat flow rate, a corresponding temperature change occurs. The rate of change of temperature is proportional to the heat flow rate times the heat capacity of the material. Now, by combining all this, we can write down a model to predict how the internal temperature changes in response to the fluctuations of the external temperature. Then we incorporate all this into a computational model and developed a web application. For this, you can upload your own data and then get a prediction about how a given enclosure will behave. So these are the locations of the web application, and also I have included some sample data in case you don't have your own data. So we can try using this data here and this web app. So first let us download the data. It is at tinyurl.com 999mcc. So let us download the data first. tinyurl.com slash 999mcc, and this is the temperature data that we want. We have data for 3 different boxes. You can try all 3 later. I will just use one. This is a polypropylene box. Data for a polypropylene box. So you can save it. This is the data that I have already downloaded. I will show how it looks like. So this data has several columns, and the first row is just the column titles. So if you are using your own data, you also need to format it like this. For the first column, you can write anything. The program just ignores it. And the first column is the time in seconds. The second column should be the internal temperature in Celsius, and the third column should be the external temperature. Uh, and this software only looks at the temperature, so it only uses the first 3 columns and ignores the rest. You can have any data you want in the next, in the third and fourth column. So here it has relative humidity, but you can just have this empty or any data here. Now let us go back and try to use the web application. So the web application is here, tinyurl.com 999tmp. So let us open it. .999tmp. So here first we have to upload the data files. So as I said, you can use your own data or the data that was given here. So I will use one of the data files on the polypropylene box. Then we need to include the name for this analysis so we don't get confused, and also this name is very important because on the way the files get saved according to this name. So let us call this pp box, and I will add my name here. You can add your own name so these files don't get confused. Then we click next. So this application takes time to upload data and do a lot of computation. So after pressing the next button, you need to be patient until the next page arrives. Now this is the data. Internal temperature is the purple data and external temperature is the orange data. Now this data is very noisy. If you look closely, it goes like this, up and down, up and down, up and down a lot because there's some overlapping data. So we first need to smooth this out. For that, we fit this into smooth curves. Here, this is the complexity of the curve that we are fitting this with. 7 is a good number. We don't want to change it. We just leave it as it is for this. But if you are using your own data, you may want to try changing this value. First, let us keep this as it is and click next to get this fitted. And I will just wait until this finishes the computation. Okay, now the program has fitted our data. The red is the external temperature and blue is the internal temperature. From now on, the program will only work with this red curve and the blue curve and not on the raw data. Okay, now again we click next. So from this blue curve and red curve, it will take some samples to make the computation. So in the next page, we can select the number of sampling points to take for this solution. So here I have 21. We can leave it as it is. It is a good number for this analysis. But again, if you are using your own data and if it doesn't work, you can try adjusting this number. So now it will compute and based on the internal and external temperature data, it will figure out the physical properties of the enclosure and make a prediction for the internal temperature using those physical properties. Okay, now it has made the prediction. This is the external temperature. Blue is the internal temperature. From the external and internal, it has figured out the physical properties of the box, and using the physical properties and external temperature, it had made a prediction for the internal temperature. And that prediction is shown in the black dashed curve. So here we can see that the prediction agrees okay with the actual internal temperature, not the actual, the fitted internal temperature, and it is in the same range. Now next we are going to the most important step. Now the black curve agrees with the blue curve, and that means the physical properties of the box has been identified in approximately correct way. So from these physical properties, we can predict how this box will behave under different external conditions, not under this particular red curve, but under any different curve for the external temperature. So let us wait for the calculation to finish. It will take some time. So here it is still going on. Now it is going to show us how the box will behave under different external conditions. Okay, so here we have the results. We have to wait a bit until the correct figure loads. So it has to load again. So we need to wait patiently a little bit. Okay, now we have everything. This is the figure that we had before. Red is the external and blue is the internal. red is the external and blue is the internal. Uh, and from this, we predict this one. Here, the red curve is a different external condition, and the black dashed curve is a prediction of how our box will behave under these conditions. So here we can adjust the red curve. So number of temperature cycles per day is 1. For 24 hours it has 1 cycle. We can increase it and see what happens. So I just clicked somewhere here. The program will take some time to finish the computation and the slider will automatically move here. But I just need to click once and just wait. Okay, the slider has moved. Let us see until the results change. Okay, now we have more cycles, around 4 cycles per day. Now you can see the buffering capacity may have slightly changed. The difference between external and internal may be more clear. And this is the amplitude of the temperature fluctuation. So this doesn't mean that the mean temperature has to be 0. It is the temperature deviation from any mean value. The absolute value does not matter in this case. So we can increase the temperature fluctuation also. We can just go there and just click once and wait for it to change. Earlier it was around 5. Now it will go up to around 10 degrees variation, 10 degrees of amplitude. So with this we can also look at how our box will behave under different conditions. So this is a 10-degree variation, and we can see whether the buffering capacity has increased or decreased, or whether the temperature fluctuation inside our box will increase as much as the external fluctuations. So this is one thing that we can do. We can use this to check how our box will behave under different conditions. Alternatively, we can go back there, we can start another instance, tinyurl.com 999 TMP, that's the temperature model. We can keep this there and start another session and use another box that we have. So that's the polypropylene box. We can add the corrugated box, the and repeat the same analysis. So here we have this data already. It is PP box, and next one we can go step by step and get a figure similar to this for the corrugated box. Then we can easily compare whether this is more suitable for our case or this is more suitable. So we have this kind of different weird figures, but this is a method of converting all of them into a consistent figure which we can analyze. So in summary, this model predicts how the temperature inside an enclosure responds to external fluctuations, and it is a consistent model of comparing different enclosures. And if you have a new box and you just do this experiment of measuring inside temperature and outside temperature, from this hopefully we will be able to predict how the box will behave under different conditions. But there are some limitations of this. Usually the temperature and relative humidity are coupled, but this model does not consider this coupling. It considers temperature separately. Um, So, w- so with this, I would like to finish. If you want to start your analysis again, you can click start again here. If you have any feedback, please send feedback to me using this email. And thank you very much for listening.